Thank you, and thank you for inviting me to speak to this conference. So 20 years ago, I was doing physics, and like most of my colleagues, I ended up in finance. And about 10 years ago, I moved to California to do what now it's called data science. I've been also running some meetups and teaching part-time at two universities in graduate programs. And of course, my employer has nothing to do with anything I say here. And I'm going to talk mostly about hype and what effect it has on our industry. And a lot of this hype is related to tools, to the tools we data scientists are supposed to use. And I have some main observations, and one of them is that I think there is some kind of mismatch because of this hype. So first of all, practitioners, I think they wish for tools that they don't really need. So in the previous talk, that was already mentioned in some way. And it also has some effect on the supply side as well. So there is a mismatch between what's available and what's advertised, but that's true for almost everything in life. But also it makes pressure on tool developers and researchers to focus on things that probably most people don't need. And my talk will be in the context of binary classification, but I think some of those observations are more general. And my talk will be some kind of series of random observations. And I'm not trying to make even more enemies. I already have enough. But I'm trying here to stimulate some kind of discussion and thinking about this kind of problems and perhaps also hope how to solve them. And I have some kind of randometer. This will, for various topics, this will show how angry I am. And if I want to summarize in a high level, so what I want you guys to part from this talk is to think about what is the most common use cases we have in data science, machine learning, and for tool developers, are we really optimizing for this kind of use cases? And I think that in many cases, we are building this kind of things that are not really optimized to the most common scenarios. And then the question is this the best allocation of resources as an industry, as developers of tools we are doing? And I think the answer is obviously no to that one. And finally, also about the demand side, that what does it mean for users? So how efficient are they? Do they lose in productivity? Do they lose in other costs? For example, in running huge Hadoop clusters. And I'm not talking about like 20% or 30% losses, but sometimes these inefficiency are like 1 order of magnitude, so easily 10x more RAM needed, 10x more training time needed, and sometimes even 100x. So these are not like small little effects. So let's talk about big data, and this is, it maximizes my randometer immediately at the beginning. So we are told that we have all this big data, and the only way to deal with it is buy a gazillion of servers and install Hadoop or lately Spark, and this is how you should deal with big data. But unfortunately for analytics, data science, data mining, machine learning, most of these tools are pretty cumbersome. And I have a different view. I think that in most cases, we can just avoid this problem. So I will argue in this talk that most people's data, after some refining, and once they get to modeling, it will fit on one big server, and we are better off just running single machine tools. So how much memory we can get? We can get easily 100 gigs for under $1,000. If we go to the cloud with a few clicks, this instance with 200 50 gigabytes of RAM has been available on Amazon for at least 3 years. Now there is this bigger instance with 2 terabytes of RAM. The other cloud providers, they have similar offerings. And let's see now how big are the data sets that people are analyzing. I don't need to introduce to this audience what's KD Nuggets. So KD Nuggets has been asking us this question for 10 years. What is the largest data set you've been working on? So I compiled all this data and put it in a GitHub repository. And I'm going to do a little bit of analysis of that. But first, I also asked on Twitter, just like a quick informal survey, what is the size of data set you're usually working with? And it turns out that, yeah, most people are working with a few gigabytes of data. There are also more formal surveys, also asking about the number of records people are working with. So most people are working with a few million records at the most. And I would say if your data is not big, don't be ashamed of. So you're probably not the only one. So maybe your data is not big, but it will get bigger, right? So if we look at this last 10 years of data collected by KD Nuggets, you can fit some kind of smoother and figure out from the coefficients that these data sets we've been working on, they have increased at the rate of 20% per year. So let's see how RAM has increased in the last 10 years. So I used here as a proxy, obviously not ideal, but still I want to get some kind of measurement on that. So the largest RAM available on EC2. And if we fit on this one some kind of trend line, we get at least 50% increase in RAM per year. So I would argue that RAM has increased faster than the data sets most people are analyzing. So actually more data fits on one server than 10 years ago. So once we got over our ego of having big data and we acknowledge that we have like gigabytes of data, it's kind of very easy to argue that the best you're off is using single machine tools like R or Python that have lots of libraries for all kinds of statistical models, machine learning, and all these kind of things, or maybe use some of these commercial products, but I grade them out because I'm more a fan of open source. And I'm not all against big data. So of course, a lot of people have big data, big raw data, so we need some kind of system to pre-process them, to refine them. But usually, once we get to the modeling, this data has been refined, reduced in size, and usually it fits in the RAM of one server. So let's go on now to machine learning. So I was interested in looking at the speed, memory usage, and accuracy of open source tools that most people are using. So again, in the binary classification setting, now I can restrict myself to 10 million records, which is the sizes I'm really interested. I think this is going by itself. But so I want to look at open source tools. At open source tools that can do binary classification with 10 million records. And why open source? Because and why off the shelf? Because they just work. So if it works for Kaggle number 1, Owen Zhang at that time, he answered this question about what magic he used to win all these Kaggles, and he said he just uses open source software that he can find freely available. So I have this GitHub repo in which I started to do. This was supposed to be like an afternoon project. It took a little bit more time. But first, what kind of algorithms should we look at? So there are these two papers from Rich Caruana's research group from 2006. They are old but absolutely relevant and not outdated. So they took a dozen of data sets, dozen of algorithms, different performance measures, and they looked at which algorithms perform the best in accuracy. So those are boosting, neural networks, random forest, support vector machines, but support vector machines doesn't scale linearly with the data. I think I should. Is your laptop put on to advance on the slide? So support vector machines doesn't scale linearly with size, so you cannot really do on 10 million records. And I want to add logistic regression, even if it's simple, just as a easy baseline. And of course, it's not only about the algorithm. So if you want to get good performance, good accuracy, you should clean your data, you should do feature engineering, you should do ensemble of various models. But in this little project, I will look at single model results. And also in the broader context, you need to do all these things that's written in the Crisp data mining process if you really want to have good models. So if we focused only on the algorithm implementations, only on the learning, then here are, I think, the open source tools that are used by most people. So I got this by talking to a lot of people, friends, looking at Kaggle forums and so on. And indeed, I did later a survey at a meetup, and those were the percentages of people using these various tools. And all these tools, they promise you like everything. So I wonder how much of this is true. So we'll see in a minute. So I took a public data set, and I'm running some experiments on public cloud so that everyone here can reproduce my results. And I'm looking at training time, RAM usage, and accuracy in binary classification. And this is not Kaggle, so I don't want to get the algo that's the best in accuracy to the last 5 digits. I want something that runs in decent time with decent memory usage, and it has accuracy as close as possible to the best. And all the code is here on GitHub, so you can run it. The data is also linked there. And I'm going for doing as little work as possible to get some results. And so I still call this benchmark like simple, limited, and incomplete. And every benchmark is wrong anyway, but maybe this has some usefulness to some. So let's look at the linear, which is like a very simple baseline. And the conclusion here is very quickly that on 10 million records, you can do linear logistic regression. You can do it with any of those tools by training in a minute or two with very little memory. So linear is trivial, but the accuracy you can get is like 0.71, so 71% AUC. So we'll see that the other models can get way better. So for one of the first models I'm looking more in details is random forest. And here there is a big difference between tools. So this would be training time, log scale versus dataset size in millions on log scale. And you can see that there is a 10x, even 100x difference between training time between different tools. So the best tools are like H2O, XGBoost, out of the ones I looked at. And those are the ones that have been written by people who know about a lot of this kind of low-level hardware optimization. So you can see this paper on arXiv about XGBoost. It has a couple of very clever optimizations, and then H2O. And a lot of this has to do in how you read the data through the algorithm so that you can keep the data as much as possible in the L2 cache, in the CPU caches. And we are very lucky, both have like R and Python packages. You can install and use them in a minute. And they are very simple to use. So accuracy, they are more or less the same except Spark. And I pointed out this to the Spark developers, and they figured out what it is. So they made some improvement, but it's still kind of broken. So you see that the accuracy doesn't grow if you go from 100,000 records to 1 million records. And I will come back a little bit to this later on, but Spark also has, it's very slow, like 10 times slower than the other ones, and also it uses like 10 times more memory. So I spent basically more time trying to benchmark Spark than with all the other tools combined. And I'm not sure if data scientists if this is the best way to spend our time. So with random forest, you can get, with some tuning, up to like 80% AUC. So remember, the linear was like 71. So on this kind of dense data with combination of numeric and categorical variables, things that show up in like fraud detection or churn on any of these other business problems, you can usually get better with a more complex model. But you can get even better with boosting. So boosting is a little bit more complex to use than random forest because it has more parameters to tune. You can also overtrain, overfit if you train too many trees, so you need to do some kind of early stopping. But the scalability is kind of very similar to the random forest, which is not surprised. It's based usually on the same tree algorithm implementation. So you can get, with a lot more work, you can get a little bit higher accuracy. So about less than a year ago, Microsoft open sourced this package LightGBM that now is actually faster than any of the packages I talked before. So if you want fast training, this is the most important thing to you, then take a look at LightGBM. It has now an R and a Python package. All right, let's get to deep learning. So how many of you guys have seen this slide? All right, so this is Andrew Ng telling us that basically deep learning beats all the other algorithms. It doesn't specifically say on everything, but this is how it kind of sounds. And indeed, on images and a lot of sequence data, deep learning has impressive results. However, I don't think that it solves really AI in general. And also, on a lot of data, for example, on this airline data, I wasn't able to get even close in accuracy to random forest or GBMs. And this is true for a lot of this kind of structured mix of categorical and numeric data that people have found in businesses. And this has been also observed in Kaggles. So in a lot of Kaggles, if you have this kind of data, it's usually XGBoost was the winner for the past 2-3 years. And deep learning was really great if you had images or some other of these text problems where deep learning is good. So my version of this Andrew Ng's curve is something like this. So yeah, don't ignore GBM. So deep learning is great, but you should also look at GBMs if you have, especially if you work in businesses. So distributed machine learning, there was here the question about distributed things. So Spark 2.0 came out about a year ago, and they added a nice data frame API. So I was hoping that they made things faster and also fixed the accuracy problems, but no, they made things even slower, and this accuracy problem is still there. So actually, I think for many of us, like Spark will be just faster on a laptop than on a cluster of any size. And don't blame the Spark developers. So distributed computing is really hard. Distributed machine learning is even harder. And you don't get the speed up all the time. So here's with H2O, for instance, on logistic regression, you get almost 5 times speed up on 5 nodes, but with random forest on like not extraordinarily large data, you might get even slowed down because the communication between the nodes slows down things. So this is Netflix. They open sourced a new shallow neural net library 2 weeks ago, and they published a blog post, and they were explaining that actually they optimized this library to work on one single server on this kind of what they call medium scale program. So 100 million rows. So if this is good for Netflix, then maybe it's good for other people as well. And inspired from this, I also asked on Twitter, like, if you can choose between your machine learning tool working on like bigger data or working faster, what do you want? And it seems like people have realized by now that big data is not their best way to get better results. But if we want faster machine learning, maybe we can go to multiple cores. So I was trying to run these benchmarks also on more cores on Amazon. So if you run on, so this is running time. If you run on 4 cores, you get this running time. If you run it on 8 cores, you get some speed up, not 2x. But if you use hyper-threaded cores, then that slows down. Or if you use a motherboard with 2 sockets, and those 8 cores are on 2 sockets, you might get even more slow. So it seems that most of these tools work well or quasi-well if you have your cores on 1 socket CPU, because because different sockets are usually tied to different memory banks. So with 16 threads, you get this much speed up. But once you start running even more cores and even more threads, you actually might slow down things. So here you can see if I use all the 128 cores, then I get a lot of slowdown versus like 32 cores or even 16 cores. So it seems like these tools don't really work well if you put them on multi-socket CPUs. And with 1 socket, kind of like 16, Arno was telling me the other day he bought a CPU with 22 cores. That's kind of the maximum you can get nowadays. So 128, you can get it only if it's multiple socket, and it may make things slower. And also there are various other interesting scaling effects. For instance, on 1 million data set, it works proportionally better than on larger data sets. So these are the kind of caching effects. And you don't get the linear speed up. So with 2 cores, you get 1.8 times faster. With 16 cores, you get maybe 6 times faster. So you don't get 16 times faster. And various tools have various scaling. So, and it also depends on the data set size. So it's kind of weird that like GBM gets with 16 cores, you get 4 times speed up. or 6 times speed up, depending on those dataset sizes, with XGBoost scales differently, and H2O again differently. So GPUs is all the rage because of deep learning. So here's NVIDIA stock price. So I guess there is a lot of demand or perceived demand for GPUs. And GPUs are great. So there has been recently some success with running databases on GPUs. Here is MapD, aggregation and join time beats all the other CPU options. And people have started to implement now XGBoost, LightGBM on GPUs, and there has been some success. So it's kind of promising. So you get similar speed as with CPUs, but unlike in deep learning where you get 100 or 1,000 times faster, for now it's kind of the same, or in some cases they found data sets where GPUs is faster, but it's not yet more than maybe 5 times faster, but it can become. So let me rant about my own work a little bit. So I didn't do all this for fun, or well, I did it for fun, but I tried to avoid. So 2 years ago, I wanted to find out these things, and I was Googling basically, and nothing really came out. So that's when I started this project. But it's more like an afternoon or weekend project. So I have some kind of wish list if someone would have the time to do all these things. So obviously you need to be, for these benchmarks to be serious, you need more data sets. So I used one data set. You need, I would say, at least 10, better 100. You need some kind of automation whenever someone upgrades a tool to run automatically, but obviously that's a lot of CPU time, so costs money. It would be nice to add more algorithms, more implementations, even for commercial tools. I have actually looked at several commercial tools, but I'm not gonna tell you because I don't wanna shame anyone. So they were really performing worse than most open source tools. And you would want to spend more time with tuning the parameters. Maybe crowdsourcing this work would work. And also, everything I said is binary classification, but it could be extended to other problems. So far, I discussed only performance, but I realized that that's probably like 1% or 5% of what's important in data science or machine learning. So what's important is kind of feature engineering. Okay, training, tuning the models, evaluating, deploying. How do we score on real-time data? How we evaluate, how we monitor. So this whole process. And I will not have too much time to get into this, but I just have a few thoughts, and then there will be a panel at 4 p.m. when we can discuss this in more details. So APIs, I really like high-level APIs. So this is some Spark code before 2.0, just for doing like one-hot encoding. So now all this is like one line of code. So you want higher-level APIs, but maybe not as high as GUIs because I think they are not flexible enough. How about cloud, machine learning as a service? So cloud is great to do training. I use EC2 a lot, but machine learning as a service, it's pretty abysmal now. So Amazon has kind of the slowest logistic regression on Earth as a service. And their machine learning as a service has only logistic regression. So no GBM, no random forest, no deep learning, no neural nets, nothing. Google thinks that machine learning equals TensorFlow, so you cannot really do GBMs or random forest. And I hate to say, but actually Microsoft has the most decent thing, but they focused a lot on this kind of GUI thing. So, and maybe this is not a problem to solve. So I agree very much with Bradford Cross, who said in a blog post that people that know what they are doing, they just use open source. And all these cloud providers, they just package those things. Real-time scoring, maybe you don't wanna score real-time. So that's the best if you can just do batch. But if you do, there are now implementations that can score like even 100 or 1,000 trees GBMs in like 2 milliseconds. So it's really great. It would be even greater if we could do this in R or Python as fast, but those solutions are like way slower, and you spend a lot of time like encoding the categorical variables or other mundane tasks. So Kaggle is great for as training wheels, but unfortunately it covers probably only like 20% of the things you need to learn to be like a data scientist or machine learning specialist. So I don't have time to go over this, but these are the things that are kind of missing if you just do Kaggle. Tuning and AutoML, there has been some work lately, and it's kind of great. I would just want to mention here one paper showing that 2 times random forest usually beats all the sophisticated Bayesian optimization schemes. We can talk about more at the panel. It's very important model understanding and accountability, but I will not talk about it. And finally, just mention evaluation matrix. All the textbooks are about AUC and precision and recall and those kind of metrics, but I would argue that what's important in a business settings is how much money your model is making when you deploy it, so how much incremental money is making. And I'm already over time by 1 minute, so we can discuss all this, come to our panel at 4 p.m. right here in the same room. Thank you very much.